This is the third and probably last lecture for Chapter 6, and we're just going to finish or pick up where we left off last time in regards to the quantum numbers. And this is the last quantum number, the fourth one. And again, all this does is allow us to differentiate between the two electrons which are found in that sublevel. Say, for example, a p. There's two electrons that could be in any particular dumbbell or orbital within there. So they can't have the exact same quantum numbers, so they give this last one a different spin. And they do have different energies that are found. So going through the same thing here. Okay. Oh, definition. Pauli exclusion principle. This states that no two electrons can have the exact same identical quantum numbers. So they're not found in the exact same location. That's the point to get across there. Pauli exclusion principle says that two electrons can't be found in the exact same location. The way I always kind of remembered it was the same address idea, that you can't have two families, theoretically, that have the exact same address. So the same thing works for electrons. So this gives us the electron configuration. So as we move through here, we have this designation as how we name these. The first symbol or letter there tells us that is the energy level. The second thing listed, the P, tells us the sublevel. It's in a P sublevel. And the 5 tells us that is the specific electron location. It's in the fifth position of the 5 potential locations. Okay. Orbital diagrams is another way to kind of designate where electrons are found or how we fill the electrons. And for example, lithium has 3 electrons, so we start off with these boxes here. So the 1s sublevel, we have to fill those first before we move into the second energy level. So we fill these with 2 electrons, giving them opposite spin directions, and move on into the second one. And the principle that goes for this is called Hunds rule. And the way I remember this one, I always call it the cupcake rule, that everybody has to get 1 before they get the second one. And we can see as far as how we're putting these together, these boxes again represent a location or an orbital that can take 2 electrons each, and you simply have to fill them in order before you put a second one in there. So, yep, this one's got 2, this one's got 2, and moving across, this one got 1, and then this one got into the next sublevel, and then everybody gets 3 before I start putting the second ones in there. So they kind of jumped ahead here a little bit, but you notice how everyone's got 1 over here, and then it goes into the next one. So they don't fill each one separately, because remember, the S's are a lower energy than the P's, so we don't go ahead and just take this one or one of these over here and put it over into this location. We have to fill the 1s and then so on down the line. You can see how it works. And then the periodic table, this just kind of shows how we read these across. So doing electron configurations and doing that other diagram is as simple as just reading across. Remember that the F's are 2 less than the energy level than what I'm in, and that the D's are 1 less than what I was, the energy level that we're in. Okay. Some weird things with the table, and this has to do with stability, is sometimes it's easier to fill an energy level than just to strictly just read across. And there's only a couple weird ones like this. Copper would be one, I believe gold is one, and chromium and molybdenum. I'll circle that one. Molybdenum is another one. And it has to do with filling that level completely. So the example I believe we use here is copper, and we do. So if we look at copper, and we might be able to see this or not, I know it's kind of small, is notice that we went from 8D8 4S2, and the S has been filled the whole time. 2. Oops, that one was kind of weird. We'll come back to chromium there. But the S has been filled the whole time. But then you get to copper, and one of the S's leaves and fills the D. So if I have the potential of filling up this D with just 1 more electron, then it's worthwhile to the atom in regards to stability to put that electron in that location. So notice over here, given the choice, I could either put that next electron in the D, or I could put it in the S, and it just makes more stable, makes a more stable atom by filling up this D sublevel as opposed to leaving it as it was. So we don't have this scenario, we have this scenario. It's more stable. And chromium and molybdenum do the same thing because they're halfway filled, and I'll just kind of put 5 lines here coming across. So it steals from the S to give this scenario for chromium and molybdenum. So they have 5 electrons in the D sublevel as opposed to leaving the S sublevel filled. So it takes one away from that. And it has to do with energies and stability. So we just already went over this, and I believe that is the end of the lecture. Very good.